Hey guys, guess who? It's me, F Train. I didn't think you'd be able to figure that out. But anyway, how's it going? It's Monday. Hope you're doing fantastic and got another lesson for y'all. I haven't checked the to see how many you did the first one. Hopefully all of you, but maybe just most of you. Anyway, I hope you're all keeping busy and doing okay. Let me know if you have any issues, any problems. I'm going to send out homework sheet number 3, I think. I'll send this out. There was a question about how to answer. Do you have to submit them individually or the whole thing? I would like you to submit the assignments individually each day. So don't, like, normally I just check the homework, at the end of each homework sheet. I would like you to submit the homework each day. So what I'll probably do is I'll just send out that. I'll send out the whole sheet, but I'll also just send out that week's assignment on the Google Docs so that it'll be more obvious. All right. So anyway, let's get into the lesson. I'm going to try to keep it relatively short. So today, all right. So today, sorry. I think after a few days, I know how to do this. All right. So today's do now is how do emission nebulae emit light. And if you didn't watch the last video and do the last homework, you might want to do that now before you do this. But we learned about different types of nebulae. We learned about emission nebula, reflection nebula, and dark nebula. And a lot of people messaged me that their favorite dark nebula was the F nebula. I'm not sure why that was such a big popular one, but anyway, I'm glad that you guys enjoyed that, and or that you guys like that particular nebula. I mean, it's one of my favorites too. But all right, so answer: emission nebula are excited by the UV light from nearby hot stars. We mentioned white dwarfs are very hot. They emit a lot of UV light, and so that UV light, those UV photons, are able to then excite the electrons in the atoms in the emission nebula, and they glow basically. In this picture here, the Trifid Nebula that you see is a good example of that. Okay, so so we saw how the interstellar medium appears to be part of pre-star formation, but how can we be sure? So today's aim is, where do stars form? If stars form in areas of molecular clouds, how much mass must be present? Well, you can imagine that even though these clouds are very low density, in order to have enough matter to form a star, they must be really, really large, because you have to have a lot of mass to form a star, right? I mean, the mass of the sun, we said, is like, almost 500,000 times greater than the mass of the Earth. So, it's a lot of mass necessary. And as we'll see, the stars are formed in these huge, giant molecular clouds. They usually start out very, very low density, as we mentioned, only a few degrees Celsius, but they have, like 10 to the fifth, which is like 100,000 solar masses. Now, of course, that's the average, maybe. So obviously, for them to have such a low density but have such a large mass, they have to be really big, and so they can have diameters like 50 parsecs. Okay, and one of these molecular clouds can give birth to literally hundreds of stars. So in order for the in order for stars to form in these huge molecular clouds that are not very dense, they have to get denser. So these clouds are going to have to contract. Okay, so the question is, what forces cause an interstellar cloud to contract? Pause. answer. And hopefully you came up with the idea of gravity. Gravity is the force that pulls everything together. Okay, so gravitational force caused the cloud to contract slowly. And when we say slow, we're talking slowly, like thousands or millions of years are necessary for a cloud to contract enough to actually, get even a pre-star formation. But as there are stars, even though there are forces that are pulling, the clouds together, what forces do you think might keep an interstellar cloud from contracting? In other words, what forces might be, kind of opposing this gravitational force? So maybe think about that for a minute. And some of those forces are magnetic fields, rotation, turbulence, thermal motion, just the molecules bouncing off of each other, etc., could prevent the clouds from contracting. Okay. Now, there's an interesting theory called the density wave theory. And one of if you ever looked at a picture of a galaxy, you'll notice that there are little arms that contain a lot of stars, and so that's kind of why they're spiral shaped, because there's these little arms which launch the stars. And back in the 60s, these two astronomers came up with this theory saying that the spiral arms of a galaxy are just regions of very high density. And so what happens is as the cloud moves through these high density regions, it allows them to achieve the density they need to for star formation. Okay, this is just one of several theories. I'm going to give you a little video. I'm going to show you this little simulation as to kind of like, you can see that sort of that density wave there, okay, that high density wave that's sort of like moving through the material as that galaxy turns and spins like that. Okay. Another theory is that sometimes there's a passing shock wave that compresses initial areas of material which trigger star formation. If you've ever seen a picture like this where this plane, usually like a fighter jet, can exceed the speed of sound, and as it goes by, it forms this shock wave, and it creates extremely high pressure that actually causes the air to condense and form like a little cloud. You can imagine similar things might happen to interstellar media. What happens with the gravitational energy from infalling material? So if you imagine that if you have all this sort of matter that's sort of collapsing and it happens gradually over, like we said, thousands or millions of years, but eventually as they get closer, you can imagine that they're accelerating all the time, because if you have a force pulling something, that object's going to accelerate. So after a while, the speed of these molecules can be relatively large, and as these molecules start to collide, they're colliding at relatively large speed. So there's a lot of gravitational energy being converted into kinetic energy, which then, infalling atoms develop thermal energy from collisions, and they heat up the clouds as they contract. So, you have all this material falling in on each other. And, you can even imagine, we've talked about like in physics class, like what happens when you take a ball and like a bowling ball and drop it on on the floor or on a rug, and it's not really going to bounce. What happened to all that energy? Well, it turned into heat. So you can imagine the same thing's happening with these molecules, and they heat up, eventually causing the cloud to glow. Okay. Once a gas cloud is contracted enough to emit black body radiation, why is it not yet considered a star? Well, we've talked about the fact that even pretty much any object that is warmer than absolute zero is going to emit some sort of radiation, and our bodies are emitting infrared radiation. So even though it's not a star yet, it can still be emitting black body radiation, probably first in the radio, then maybe in the infrared wavelengths. And this is called a protostar. Okay, so a protostar is a prestellar object that's hot enough to radiate infrared radiation, but not hot enough to ignite nuclear fusion. We talked about the fact that nuclear fusion, we're talking millions Kelvin, 10 million Kelvin or so to ignite nuclear fusion. So you can imagine that something could be a lot cooler than that. Even the stove, like if you have one of those electric stoves or a toaster, those things glow, even though they're not even nearly hot enough to ignite nuclear fusion. And then, so there's this big, cloud of gas that's sort of usually spinning. We'll talk about that in a minute. But as these things are falling in, you have this sort of, gas on the outside that's feeding this protostar. As, more and more stuff falls in, it's sort of feeding this protostar. Now, why would a protostar be surrounded by a disk of matter? And the reason is that it's spinning. If you've ever watched a pizza maker make a pizza, you start spinning the ball of dough and it starts to flatten out. And that's basically what's happening here is, the disk of gas flattens out from the centripetal force, or, you can think of it also as like centrifugal force that sort of causes it to spread out. Planets are usually formed in these disks, and eventually the star will become visible after it blows away that sort of outer. So it has this sort of halo around it, and eventually it will sort of blow that gas away, and you'll actually be able to see the star. Now the question is, what force blows away this this gas and dust? So pause, think about that for a second. Talk to your homies about that. And so hopefully you will recognize that, this is when nuclear fusion is starting to ignite. Now you have a tremendous amount of force that's going to blow this, this dust and gas away, okay? If different sized stars start off on different parts of the HR diagram, what does that tell us about the star's movement along that diagram? Well, you can see that, we talked about the fact that on the HR diagram, a main sequence star will, well, actually, if you look at the protostars are going to start out large and cool, right? So kind of like the opposite of after a star dies and it expands like a red giant. Well, this is before it's also kind of like a large, cooler object, which is then, if you follow my pointer here, like this star is going to sort of move toward the main sequence. And so you can see, depending upon where a cloud starts in terms of its size and luminosity and mass, etc., that will determine where that star is going to begin its life on the main sequence. Okay. And so where's the sun? That looks like the sun probably started maybe around here and sort of moved along this path and eventually ended up on the main sequence. Okay. Stars assume an initial position on the main sequence due to the size of the interstellar cloud from which they were formed. Okay. I have a couple videos that I probably would have shown you if we had class. So what I'm going to do is I'm just going to link those videos onto the Google Classroom page. They're short, like a couple minutes each. That's Pistol. By the way, Pistol had a birthday last week, and the mailman's coming, so I better sign off here. So anyway, like I said, hope you guys are doing well. Miss you guys, definitely miss you. Hopefully you're getting into somewhat of a routine now, and before you know it, this will just seem like normal, right? Hopefully not. But anyway, miss you guys and talk to you soon.